Welcome to Microlecture 40, which is a video problem set on SN2 versus E2 reactions. Okay, so none of this is new material here. What we're doing is just practicing deciding whether the reaction is SN2 or E2, and then writing out the mechanism, and some generic mechanisms are in the upper right-hand corner to differentiate SN2 from E2, just as a reminder. And then lastly, to predict the major organic product from each reaction. So the first one is the reaction of sodium cyanide with this alkyl halide. Whenever you see a sodium, put a plus. So the nucleophile is actually this cyanide anion, and it's going to go in for the attack at the partially positive carbon atom and kick out the leaving group as a bromide. Okay, so I'm just going to predict the major organic product in each case, and so just the carbon-containing product. I'm not going to write bromide. And so I would expect this reaction to proceed by SN2 reaction, and I would expect this product. Keep in mind DMSO is just a solvent. It's a polar aprotic solvent, and there's several of them in this problem set to get you used to seeing the solvent written as part of the problem. The other thing that it is important to include here, if you're asked to do it, is to indicate by which mechanism this reaction is proceeding, and in this case it's SN2. The next example is that of potassium ethoxide as a strong base. Whereas cyanide was a great nucleophile, it liked to attack a carbon atom. Potassium ethoxide is a strong base, and so it would prefer to attack a proton. And so I'm going to find beta protons. I'm going to label them in. And I know that my goal, if I can, is to generate the most stable alkene possible. And so it's for that reason that I'm going to attack this proton, kick the electrons in to form the double bond, and lose the leaving group. As my major organic product, I would expect to form my carbon-carbon double bond here. And the reason for that is because tri-substituted is more stable than the di-substituted alkene product I would get if I had chosen the beta protons that were towards the bottom of the structure. This reaction proceeds by some more examples. We have cyanide as a nucleophile. Again, cyanide would rather attack carbon than a proton, and also we're seeing a solvent, DMF, which is aprotic. It's a polar aprotic, and that's a red flag for SN2 reactivity. Okay, so the cyanide can go in for the attack at the partially positive carbon atom and kick out the leaving group, leaving me with a major organic product, which looks like this. Notice that you always invert the stereocenter. So if my leaving group was on a wedge, I must draw the nucleophile that came in attached on the dash. So all R centers go to S, and S centers go to R through inversion of stereochemistry with SN2 reactions. The next example is a strong base, potassium ethoxide. You notice that alkoxides are typically run in a solvent that is the conjugate acid of this base, which is why we run this reaction in ethanol. And you also notice that that's a protic solvent, and we would not want to do an SN2 reaction with that. So strong base and protic solvent. I'm going to take the strong base and abstract a beta proton. Well, if I draw this beta proton, I see it's on the same side as the leaving group, and that can't be. With E2 reactions, there's an anti-geometry requirement. So I'll draw in these two beta protons, and I see that the only one that's available for me to take, which is anti to the leaving group, is this one. So the electrons kick in, I lose my leaving group, and my major organic product puts the double bond right here. We have to form this di-substituted alkene, instead of the tri-substituted alkene because of this anti-geometry requirement. Right, so that went by E2 reaction. Another example here, sodium iodide. Iodide is a great nucleophile. It's a very polarizable, huge atom that would prefer to attack a carbon than a proton. And so I would expect to see SN2 reactivity. Also, we're seeing this aprotic acetone solvent. And when we see aprotic solvents, that's another sign that it's probably SN2, not E2. And so the iodide is going to come in and attack at this partially positive carbon atom and kick out the leaving group. And that's going to generate my major organic product. So all the rest of this structure just gets redrawn exactly as you see it. Okay. Otherwise, the answer is wrong if the structure is wrong. We see a stereocenter here, and the chemistry did not happen at that stereocenter. So that stereocenter remains the same, and the group that's now coming off of here is iodine. We kicked out the good leaving group, the mesylate. And this is my major organic product, and it happened via SN2 reactivity. Here's a few more problems. We've got sodium methoxide. That's a strong base run in a protic solvent. These are the signs that it's going to be an E2 reaction, so I'm going to draw in any beta protons that exist. There's actually 3 over here. But I am going to choose, my base is going to choose this beta proton because that's the route that gives me the most stable or most substituted alkene. I'm also going to draw it trans, or E, because that would be the most stable stereoisomer. Okay, to have these high priority groups as far away from each other on the double bond. Because there's no constraints here. There's no bulky base, there's no problem with achieving an anti-geometry, and so the goal is to form the most stable alkene that you can when you're doing an E2 reaction. The next example is an example of a bulky base, but it has little consequence because of the nature of the alkyl halide we're reacting. Bulky bases can't get into highly substituted regions on molecules or more substituted regions, but this is a primary alkyl halide, and so there's only a couple of beta protons. They're equally accessible, and so the base is going to abstract one of them, whichever one is anti, and generate the major organic alkene product via E2. I wanted to show you another example of a bulky base. Negative charge on nitrogen is a lot like a negative charge on an oxygen. This is going to be a strong base, but we've got these big bulky isopropyl groups, and so just like a tert butoxide, which you have seen before, this is also a bulky base. So I see that I've got beta protons here, and I've got beta protons here, but being that this base is very cumbersome, it's not going to be able to get in and grab a beta proton from a carbon that's attached to 2 other carbons. It's going to instead grab onto the most accessible proton, the first one it sees when it approaches the structure, and so that would be on a beta carbon that has just 1 other carbon attached. Electrons would kick in to form the carbon-carbon double bond, and the bromide is lost as a leaving group, generating actually the less stable alkene because of this bulky base. So if we kind of compare to the situation at the top of this page, when you're using an ordinary non-bulky base, you can form the more stable alkene, but bulky bases sometimes prevent us from being able to form the more stable alkene.